Let's move on to the new article, that is characteristics of electromagnetic waves. And this is the same figure what we have observed when we have determined the directions of electric fields and magnetic fields. And here the direction of propagation, that is perpendicular to this particular factor, is perpendicular to E cross B. So it is perpendicular to E also as well as of B. Now we can see an electromagnetic wave is propagating only in the x direction. So here the electric field is lying in the xy plane and is parallel to y-axis. Whereas if you see about the magnetic field B at initial stage, then it is in the xz plane and that is also parallel to z-axis. Now, the first characteristic for electromagnetic waves is a task in which we have to represent electromagnetic waves in the form of equation. So it is the representation in the form of equation. So here we will consider one electromagnetic wave, and at time t I am taking some components of electric field as well as the components of magnetic field. But here we have seen that for the electric field it is parallel to y-axis, and so the components in x direction as well as the components in z direction will be 0. So E components or the components of electric field and Ex and Ez, which are respectively of x and z component of electric field, both are 0 because there is no propagation in, or there is no existence of electric field in x and z direction, and hence I can write down my equation for electric field or the y component of electric field. Ey is equal to E0 sine of omega t minus kx. So this is the first equation, and E0 is the value of electric field at time t is equal to 0. And now in the vector form, so E vector is equal to Ey into j cap, that is equal to E0 sine of omega t minus kx into j cap, and this is the basic equation for describing any wave. So amplitude and angle. So these two things are very important. But here, what is the omega, what is this k, it is necessary to understand, and therefore omega is the angular frequency. It is written as 2 pi f, and the small k is the magnitude of wave vector K, that is equal to twice pi over lambda. And now I can write down one equation for speed of light that is written in the form of lambda into f. So now I can write down the value of lambda from this equation. So it is twice pi over k into the value of f from this equation, that is omega over 2 pi. And hence this 2 pi is cancelled out, that is equal to omega by k. And this is the third equation in our representation number 1. And similarly, this is the case of electric field. And now for the magnetic field, only the z component is there because it is parallel to z. So bx and by both will be 0, and bz I am directly writing for vector notation, bz into k cap, that is equal to b0 sine of omega t minus kx into k cap, and that is your equation number 4. And this way we can represent electric field as well as the magnetic field. And here it is better that you should write Bz only P, because Bz is the component. Now comes to the second important characteristics of electromagnetic waves. So the second characteristic is in this way. In electromagnetic wave, the relation between the magnitudes of electric field E and magnetic field B is given by, now we will write in terms of magnitude. So here there will be no vector sign. So it is given by E over B is equal to small c. And here you should remember that electromagnetic waves are self-sustaining. They are self-sustaining oscillations of electric and magnetic fields in free space or vacuum. And now, one important point which should be remarkable over here is that the constituent particles of material are not oscillating with the vibrations of electric and magnetic field. So there is no effect of electric field and magnetic field vibration on the constituent particles of material. And now we will switch on to one important meaning from this? So we can say that electromagnetic waves are non-mechanical waves. The third point related to the characteristic is given like this way. The velocity of electromagnetic waves in free space is given by small c is equal to 1 over under root mu 0 epsilon 0. So this is the first equation in our characteristic number 3, and this fact was derived by Maxwell using the equations of electric fields and magnetic fields. Here if we look at the values of mu 0 and epsilon 0, so mu 0 is equal to 4 pi into 10 to power minus 7 Newton upon ampere square, and this is, remember, the permeability of free space. Now epsilon 0 is having the value 8.85419 into 10 to power minus 12 coulomb per Newton into meter square, and this is the permittivity of free space. So these both are different. This is permeability and this is permittivity. And using these two values, I can find out the value of C comes out to be 2.99792 into 10 to power 8 meter per second, which is nearly equal to 3 into 10 to power 8 meter per second, which is very equal to the velocity of light in a medium. That means the velocity of EM wave passes through any medium is given by V is equal to 1 over under root of mu epsilon. So this is the second equation in this particular characteristic. And here remember, this is permeability of the given medium and epsilon is the permittivity of the medium. So it is necessary to define. And epsilon is the permittivity of the medium. Now with this, the velocity of light means C is depending upon the electric and magnetic properties of the medium. And for any medium, if we look at the relative permeability, that is denoted by mu subscript r, and it is basically the ratio of permeability of the medium and permeability of free space, means mu 0, and also the relative permittivity, that is epsilon r is equal to epsilon upon epsilon 0. So this is third and fourth equation in our characteristic explanation. And now, if I denote the constant epsilon r as a constant k, then this is the constant, or we can say the dielectric constant of the medium. And hence from the equation number 2 actually, we have the values like this. V is equal to 1 over under root mu e. Now from the equation number 3, you can see that the value of mu is mu r into mu 0, and the value of epsilon is epsilon r into epsilon 0. So substituting this way, mu r, mu 0, epsilon r, epsilon 0, that is equal to 1 over under root of mu 0 epsilon 0 under root of mu r epsilon r, that is equal to 1 over under root mu r into epsilon r, but we know that 1 over under root mu 0 into epsilon 0 is small c. So small c divided by under root of mu r. But what is the value of epsilon r? Is equal to capital K. And hence this is the final equation, equation number 6. And now we can actually find out the refractive index of the medium. It is given by eta is equal to C over V is equal to under root of mu r epsilon r, that is equal to under root of mu r into k, and that is equation number 7. And with this our characteristic is over. But you should consider one thing, that the velocity of electromagnetic waves in free space, means c, is an important fundamental constant. And now let's move on to the fourth characteristic of EM waves, that electromagnetic waves are transverse waves. And the transverse nature we have studied in the earlier article. Now the fifth one, electromagnetic waves possess energy and this energy can be carried from one place to another. And here, if you want to find out how to carry energy from sun to earth, then electromagnetic waves are responsible for that. So electromagnetic waves carry energy from the sun to the earth. And so it is possible to making the life on the earth. Now the sixth reason or the sixth characteristic is in this way. Electromagnetic waves exert pressure on a surface when they are incident on it. And this pressure is known as radiation pressure. This imparts linear momentum to the surface. That means now the total momentum is distributed over the surface. And now let's understand it. Suppose delta U is the energy of electromagnetic waves These waves are incident on a surface area A and the time taken for incident on it is delta t. So it is time interval basically. And the direction of electromagnetic waves is normal to the flow of energy. And now we are assuming that the energy is completely absorbed by the surface and then the momentum which is imparted on the surface is given by delta U over c. The c is velocity of light and this is for completely absorption. That means there will be no reflection, which also exerts, and this particular momentum also exerts the radiation pressure Ps on the surface. Now let's go through the seventh characteristic. The seventh characteristic, it is related to the electromagnetic field. So electromagnetic fields will generate in the region where the electromagnetic waves propagate. That means the electromagnetic energy, because each field is consisting of some energy. So here electromagnetic energy per unit volume so basically is the energy density is given by rho is equal to density from electric field and density for magnetic field. So this is the first equation in our this characteristic analysis, that is equal to, now the density of electric field we have earlier seen, it is very much related to the kinetic energy, 1 by 2 epsilon E square, and the density of magnetic field is given by b square over 2 mu 0. This is result number 2. And here rho is energy density associated with electric field and this is associated with magnetic field. Now, if we apply or if we obtain this relation for inductor and capacitor in the stationary field, then here electric and magnetic fields are oscillating as per sine or cosine function, and so it is necessary that we should consider the RMS value. So this is the basic concept. Why we use the RMS values? Because in the stationary field, if you look at this electric field and magnetic field, then they are oscillating either a sine or cosine function. And so for stationary fields, I have to take a constant value. Therefore, energy density rho is equal to 1 by 2 epsilon 0 E RMS square plus B RMS square upon twice mu 0. That is equation number 3. Now, c square, if you look at the velocity of free space, is given by 1 over mu 0 epsilon 0. And from this, I can write down the value of mu 0 as c square epsilon 0 raised to minus 1. It is equal to 1 over c square into epsilon 0. Which value I can substitute in this relation, but B RMS is equal to E RMS over C. Because we have earlier considered one relation in the characteristic number 2 that E over B is equal to C. So same relation I am using over here. So by substituting these two results in equation number 3, we will get in this way the answer rho is equal to, there is no change in the first term, it is very similar, 1 by 2 epsilon 0 E square RMS plus b square upon 2 mu 0. So b square RMS is square RMS over c square divided by 2 mu 0. So 2 and mu 0 is having the value 1 over c square epsilon 0. So this c square is cancelled and the final result will be 1 by 2 epsilon 0 E square RMS plus 1 by 2. Now this denominator of denominator will come into the multiplication with numerator. So it is epsilon 0 E RMS square. Therefore, rho is equal to epsilon 0 ERMS square. Similarly, you can obtain one relation in terms of the magnetic field BRMS square divided by mu 0, and so these two are the energy density for electromagnetic waves. Now the eighth result is very much important. The intensity of radiation. That is I, is defined as the radiant energy passing through unit area normal to the direction of propagation. In 1 second. So this is the definition of intensity of radiation, and its mathematical formula is given in this way. Therefore, I is equal to the radiant energy per given time per unit area is equal to energy upon time is power, and the area is as it is. So basically intensity is nothing but the power per unit area. If you look at this figure, then the radiation energy is passing through a unit cross-sectional area in 1 second, which is confined within a volume of length equal to C. Now if rho is the energy density, then the energy in the above volume is rho into C, because C is the length of this uniform cross-sectional area. Therefore, this is the energy. And intensity is now defined as the energy which we want. That is equal to, now substitute the value of rho in terms of E square RMS into C. So this is the first equation. Similarly, we can obtain I is equal to B square RMS into C over mu 0. And now come to the last characteristic of electromagnetic waves. E cross B gives the direction of propagation of electromagnetic waves, which we have seen in the article number 3.2 and also in this particular article. And now we will solve some illustration related to the discussed theories.